Look up at the night sky. What do you see? Stars, galaxies, endless darkness. But what if I told you the universe isn't just scattered lights and empty space, but a vast, intricate tapestry woven together by invisible threads? These threads, cosmic web filaments, are the hidden scaffolding of existence, stretching billions of light years across the cosmos, binding galaxies together in a delicate dance of gravity and mystery. Picture this, an unimaginably colossal network of glowing tendrils, thinner than a spider's silk yet stronger than any force we know, holding the universe itself in place. How is such a thing even possible? For centuries, we've gazed at the stars and wondered how everything fits together. Now, science reveals the answer isn't in the stars alone, it's in the spaces between them. These cosmic filaments, invisible to the naked eye, are the universe's secret architecture, channeling dark matter, birthing galaxies, and shaping the fate of everything we see. Yet for all their power, they're one of the cosmos's greatest unsolved puzzles. What lurks within these filaments? How do they dictate where galaxies form? And why do some regions of space remain eerily empty? And perhaps the most haunting question of all, could these mysterious structures hold clues to the ultimate fate of our universe? That's exactly what we're about to explore. Over the next journey together, we'll unravel 25 mind-bending mysteries hidden within these cosmic filaments, from their ghostly origins in the Big Bang to their chilling connection with dark energy, from the way they warp time itself to the bizarre celestial phenomena born in their shadowy embrace. This isn't just a story about far-off wonders. It's a story about us because every atom in your body, every star overhead, exists because of this invisible cosmic web. So let's dive deep into the unknown, where the answers will leave you breathless and the questions will linger long after the screen fades to black. The universe's greatest secrets are waiting. Think of the universe not as a random scattering of galaxies, but as something far more organized, like the delicate threads of a spider's web, glistening with dew in the early morning light. Only instead of silk, these threads are made of galaxies, gas, and something far more mysterious, dark matter. This is the cosmic web, the hidden architecture of everything that exists. Picture a vast, interconnected network where colossal filaments, some stretching hundreds of millions of light years, act like cosmic highways, linking dense galaxy clusters at their intersections. Between them, enormous voids, empty regions so vast they could swallow thousands of galaxies without a trace. Scientists call this the large-scale structure of the universe, and it's eerily similar to another intricate system, the human brain. Just as neurons connect through thread-like axons to form thoughts and memories, galaxies are strung along these filaments, bound together by gravity's invisible hand. But here's the strange part: most of this web isn't even made of the stuff we can see. Up to 85% of it is dark matter, an enigmatic substance that doesn't emit light or energy, yet its gravitational pull shapes the entire cosmos. Without it, galaxies would drift apart and this grand cosmic web would unravel. What's even more astonishing is how this structure formed. In the aftermath of the Big Bang, tiny ripples in the fabric of space-time, fluctuations so small they were quantum in scale, slowly stretched and magnified over billions of years. Gravity did the rest, pulling matter into those dense filaments and leaving the voids nearly empty. It's like watching a city grow. First, small paths become roads, roads become highways, and where they intersect, skyscrapers rise. In the universe, those skyscrapers are galaxy clusters, the brightest, most massive cities of stars. Yet for all we know, this cosmic web holds even deeper mysteries. Why do some filaments glow faintly with superheated gas, while others remain dark and silent? How do galaxies move along these threads as if drawn by some unseen current? And could this structure, this blueprint of the universe, hold clues about how everything will end? One thing's certain: the cosmic web isn't just the backdrop of the universe. It's the stage, the script, and the director all at once. One of the greatest puzzles in modern cosmology isn't just what the cosmic web looks like, it's how something so enormous, so perfectly structured, could emerge from the chaos of the early universe. These filaments, stretching like bridges between galaxies, aren't just massive, they're ancient, tracing back to a time when the cosmos was nothing more than a seething, formless sea of energy. So how did this intricate web take shape? The answer lies in a cosmic tug of war between the universe's most mysterious forces. Rewind nearly 14 billion years to a moment just after the Big Bang. Space wasn't empty, it was a roiling ocean of hot plasma, buzzing with particles and energy. But hidden in that chaos were tiny ripples, imperfections so small they'd be invisible to even the most powerful microscope. These were quantum fluctuations, random variations in density left over from the universe's birth. And as the cosmos expanded, those microscopic wrinkles didn't fade, they grew. Gravity, that relentless sculptor, began amplifying them, tugging ever so slightly harder on regions where matter was just a bit more crowded. Over millions of years, then billions, those minuscule differences snowballed into vast cosmic highways, pulling matter into filamentary threads and leaving empty voids in between. But here's where things get even stranger. Ordinary matter, the stuff we see, wasn't the real architect of this web. It was dark matter, that invisible, ghostly substance that neither emits nor reflects light. Because dark matter doesn't interact with electromagnetic forces, it wasn't slowed down by the intense radiation of the early universe like normal matter was. Instead, it moved freely, collapsing first into a sprawling network of filaments under gravity's pull. Ordinary matter simply followed, flowing into this pre-built scaffold like water filling cracks in stone. Without dark matter's unseen hand, the cosmic web wouldn't just look different, it might not exist at all. Yet even with dark matter's starring role, there's still fierce debate among scientists about the finer details. Some theories suggest that magnetic fields woven through the early universe helped guide gas into filaments, giving them their glowing, thread-like appearance. Others argue that cosmic inflation, the universe's rapid expansion in its first moments, might have imprinted these structures like a fingerprint, setting the stage for everything that followed. And then there's the question of timing. Did filaments form all at once, or did they grow piece by piece, merging and evolving as galaxies clustered along them? The deeper we dig, the more questions arise. Why are some filaments dense and bustling with galaxies, while others stretch like ghostly tendrils through near-empty space? Could there be undiscovered forces at work, shaping the web in ways we haven't even imagined? Every answer pulls us further into the mystery, revealing just how much we still don't understand about the universe's grand design. One thing's certain, these filaments aren't just relics of the past, they're blueprints, written in the language of dark matter and gravity, telling the story of how everything, including us, came to be. If the cosmic web filaments are the universe's hidden skeleton, then dark matter is the ghostly marrow inside them, elusive, invisible, yet holding everything together. Here's the startling truth. Roughly half of all dark matter in the universe isn't floating freely in the voids or locked inside galaxies. It's concentrated in these filaments, woven into their very fabric like threads of shadow. But if we can't see it, how do we know it's there? And why does it cluster so densely along these invisible highways? The answer lies in a phenomenon as elegant as it is bizarre: gravitational lensing. Imagine space-time as a stretchy rubber sheet. When light from distant galaxies travels toward us, it doesn't always move in a straight line. It bends around massive objects warped by their gravity. Even though dark matter doesn't emit or absorb light, its gravitational pull is so strong that it distorts the path of light passing through it, like a magnifying glass warping the image behind it. By studying these subtle cosmic mirages, astronomers have mapped the unseen mass of filaments, revealing their staggering dark matter content. Some filaments act like cosmic funnels, channeling dark matter with such density that they warp the light from thousands of galaxies behind them, stretching their images into faint, smeared arcs across the sky. Yet this discovery only deepens the mystery. Why does dark matter, which theoretically should spread more evenly, pile up so dramatically inside filaments? One leading theory suggests it's a relic of the universe's earliest moments. In the aftermath of the Big Bang, dark matter's lack of interaction with radiation allowed it to collapse faster than ordinary matter, forming vast river-like flows where gravity could concentrate it. Ordinary matter, slowed by its constant collisions with light, later flowed into these pre-existing channels, building the luminous galaxies we see today along the filament's edges. But this doesn't fully explain the bizarre clumping patterns scientists observe. Some filaments seem to have dark matter spread smoothly, like ink diffusing through water, while others contain dense, knotty regions where dark matter pools unpredictably, almost as if some unseen force is sculpting it. Even stranger, the distribution of dark matter in filaments doesn't always match what computer simulations predict. When physicists model the universe's evolution, their virtual cosmic webs often appear more uniform than the real thing. The discrepancies hint at gaps in our understanding. Could dark matter interact with itself in ways we haven't yet imagined? Or are we missing a piece of gravity's puzzle, an extra rule that governs how matter clusters on the largest scales? Some researchers speculate that filaments might house exotic, dense pockets of dark matter, regions so extreme they could even warp time itself. Others propose that dark matter isn't a single substance but a mix of particles with different behaviors, some sticky, some fast-moving, all weaving together to form this invisible tapestry. What's certain is that these filaments aren't passive structures. They're dynamic, evolving conduits funneling dark matter, and with it the fate of galaxies across the cosmos. Every unexplained clump, every anomalous lensing effect, is a whisper from the universe's hidden blueprint, challenging us to listen closer. And until we crack dark matter's code, the filaments will keep their secrets draped in shadows just beyond our reach. But here's a cosmic plot twist that still leaves scientists stunned. Half of the ordinary matter in the universe has gone missing. Not dark matter, not exotic particles, but the very atoms that make up stars, planets, and even our own bodies. This is the missing baryon problem, one of the most baffling gaps in our understanding of the cosmos. Baryons, the building blocks like protons and neutrons, should be everywhere, yet when astronomers tally them up, they can only account for about half of what the Big Bang's leftovers suggest should exist. So where did it all go? The answer might lie hidden in the cosmic web's faintest, most overlooked corners. For decades, researchers assumed this missing matter was simply too diffuse to detect, scattered thinly across the voids between galaxies. But recent breakthroughs have revealed something far more intriguing. It's not hiding in the emptiness. It's simmering inside the filaments themselves, trapped as ultra-hot gas with temperatures soaring into the millions of degrees. Gas this hot doesn't glow in visible light. It's only detectable as a faint whisper in the X-ray spectrum, like a ghostly fingerprint on the universe's window. Telescopes like the European Space Agency's XMM Newton have finally begun picking up these elusive signals, tracing the glowing outlines of filaments that were once invisible to us. The data is staggering, thread-like rivers of searing plasma, weaving through space with densities so low you'd find just a handful of atoms in a volume the size of your living room, yet stretching so vast that collectively they could account for every missing atom in the cosmos. What's even wilder is how this gas got so hot. One leading theory points to the violence of the cosmic web's formation. As dark matter's gravity pulled matter into filaments over billions of years, ordinary gas didn't just flow smoothly. It crashed into itself at colossal speeds, creating shock waves that heated it to temperatures rivaling the cores of stars. Picture a cosmic traffic jam where particles accelerate to near light speeds, colliding so fiercely they ignite into an invisible inferno. But there's a catch. This gas is so sparse that it barely interacts, leaving it shimmering faintly between galaxies like a phantom glow. Yet these discoveries only deepen the mystery. If filaments are brimming with this ultra-hot gas, why does it refuse to cool down and clump into new stars? Some simulations suggest magnetic fields threading through the filaments might act like insulation, trapping heat for billions of years. Others propose that dark energy's relentless push keeps the gas too agitated to settle. Even stranger, certain filaments seem to be missing this X-ray glow, entirely hinting that the universe's missing matter might be distributed in ways we still can't predict. Every detection raises new questions. Could this hidden gas hold clues about how galaxies fuel their growth, siphoning matter from these faint tendrils? And if we've overlooked half the universe's ordinary matter for this long, what else might be lurking in the cosmic web just beyond the edge of our vision? One thing's clear: the filaments aren't just the universe's scaffolding. They're its attic, its shadows, its secret vaults, and we've only just begun to peer inside. Some cosmic filaments feel as cold as the void between galaxies, barely a whisper above absolute zero, the coldest temperature possible in the universe. Others blaze hotter than the cores of stars, searing at millions of degrees. How can the same cosmic threads, woven from the same fabric of space, swing between such impossible extremes? This isn't just a curiosity, it's a cosmic contradiction that defies everything we know about how heat spreads. Take the Boötes void, a sprawling emptiness where filaments stretch like frozen rivers. Here, gas lingers at just 2 or 3 degrees above absolute zero, so cold that atoms nearly stop moving altogether. Yet less than 1 billion light-years away, in the Perseus-Pisces filament, matter crackles at temperatures rivaling supernovas. The difference, it comes down to density, or rather, the lack of it. In the emptiest regions, gas particles are so sparse they almost never collide, trapping them in a deep freeze that's lasted billions of years. But where filaments knot together near galaxy clusters, chaos reigns. Gas slams together at thousands of miles per second, superheated by shock waves as violent as any stellar explosion. But here's the real puzzle: these extremes exist side by side. The same filament can have icy stretches and scorching hotspots, sometimes just a few million light-years apart. Traditional physics says heat should balance out over time, smoothing these wild swings. Yet the cosmic web clings to its temperature gaps like a stubborn secret. One theory blames dark matter's shadowy influence, its gravitational pull might herd cold gas into isolated pockets while funneling hot gas into turbulent whirlpools. Others point to cosmic rays, high-energy particles that could act like invisible blowtorches, reheating gas long after it should have cooled. Then there's the X-ray mystery. Some filaments glow faintly in X-rays, revealing their million-degree plasma, while others, just as massive, stay eerily dark. Why? Magnetic fields might play a role, trapping heat in some threads while letting it leak away in others. Or perhaps dark energy, stretching space itself, stirs the gas enough to keep it simmering. Whatever the cause, these temperature swings aren't just quirks, they're clues. Hot filaments might birth galaxies by condensing into stars, while frigid ones could preserve primordial gas from the dawn of time. The cosmic web's thermostat is broken, and that's exactly what makes it so fascinating. Until we understand why, we're left staring at a universe that refuses to play by the rules, a place where fire and ice exist in the same breath, woven into the dark threads of everything. Among the cosmic web's most baffling features are the ghostly magnetic fields that weave through its filaments invisible threads of force strong enough to bend particles, yet so subtle we almost miss them entirely. These fields shouldn't exist at such vast scales. Magnetism, after all, is supposed to weaken over distance, fading into irrelevance across the emptiness between galaxies. Yet here they are, stretching millions of light-years along filaments with an eerie uniformity, as if the universe itself traced them with a cosmic ruler. Where did they come from, and why do they refuse to fade? One leading theory takes us back to the universe's first moments. In the seething chaos just after the Big Bang, quantum fluctuations might have twisted the newborn cosmos into a primordial magnetic field, a relic imprint weaker than a fridge magnet but stretched across the entire sky. As the universe expanded, these fields could have been amplified by the turbulent motions of gas flowing into filaments, like invisible ink smeared across the cosmic web. If true, this would mean we're detecting fingerprints from the dawn of time, preserved in the magnetic threads of space itself. But there's a rival explanation that flips the script. Maybe these fields weren't born in the early universe at all. Instead, they could be the fallout from later cosmic violence, supernova and quasar outbursts spewing magnetized plasma into intergalactic space, where it tangled into filaments over billions of years. Picture a wildfire spreading embers, galaxies acting as arsonists, seeding magnetism far beyond their borders. This would explain why some filaments glow faintly with polarized light, their magnetic fields aligning in ways that suggest a turbulent, star-forged origin. Yet both theories collide with a glaring inconsistency. The fields are too uniform. Primordial magnetism should have fractured into patches during the universe's expansion, while galactic outflows would create a chaotic patchwork of strengths and directions. Instead, measurements reveal fields eerily similar in strength, around a millionth of Earth's magnetic field, whether we look near the Milky Way or halfway across the observable universe. It's as if some unseen process keeps fine-tuning them, a cosmic calibration we don't yet understand. Even stranger, these fields might be doing more than just decorating the web. Simulations suggest they could act like cosmic highways for high-energy particles, guiding cosmic rays across unimaginable distances. Some researchers speculate they even influence how galaxies form, with magnetic pressure subtly resisting gravity's pull in certain regions. But until we unravel their origins, these fields remain one of the web's greatest enigmas, a silent, invisible force threading through the dark, shaping the universe in ways we're only beginning to glimpse. Galaxies aren't just scattered randomly along cosmic filaments. They seem to be listening to some unseen cosmic conductor, aligning themselves with these invisible threads in a way that defies everything we thought we knew. Near filaments, galaxies don't just drift aimlessly. They tilt, rotate, even stretch their shapes to match the filament's axis, like iron filings lining up with a magnet. This isn't just a curious pattern, it's a full-blown cosmic rebellion against our most trusted models of galaxy formation. According to traditional theories, galaxies should spin and orient themselves based on local turbulence and mergers, their axes as unpredictable as dice rolls. Yet observations tell a different story. The Hubble Space Telescope and other instruments have caught galaxies red-handed, their disks and bulges suspiciously aligned with nearby filaments as if pulled by some invisible hand. Some spiral galaxies even appear to be rolling like logs along these cosmic highways, their rotation axes locked parallel to the filament's length. The effect is strongest within about 50 million light-years of a filament, fading with distance, but that only deepens the mystery. Why would galaxies millions of light-years apart coordinate their behavior like this? The leading suspect, dark matter's hidden script. Simulations suggest that as filaments formed, dark matter didn't just clump, it flowed in vast, swirling rivers, spinning entire strands like cosmic whirlpools. Ordinary matter, including gas and nascent galaxies, may have gotten caught in this spin, imprinting alignment patterns that persist billions of years later. If true, this would mean dark matter doesn't just sculpt the universe's structure, it choreographs galactic motion on scales we're only beginning to comprehend. Yet this explanation opens new paradoxes. If dark matter's spin imprints alignment, why do some filaments show galaxies aligning while others don't? Even more puzzling, certain regions show galaxies aligned perpendicular to filaments, as if repelled rather than attracted. Some theorists propose that competing forces like tidal interactions between clusters or residual momentum from the Big Bang might be overriding dark matter's influence in these areas. Others speculate that dark matter itself could have substructure with different flavors exerting competing torques on galaxies. Then there's the eerie case of elliptical galaxies. Unlike spirals, which often align their spin, ellipticals tend to stretch their shapes along filaments like taffy pulled from both ends. This suggests filaments might not just orient galaxies, they could be reshaping them, stretching and compressing them over cosmic time through gravitational tides we barely understand. The implications are staggering. If galactic alignment is written into the Cosmic Webs blueprint, it could mean that a galaxy's fate, its shape, spin, even its star-forming potential, is partly decided by which filament it's born near. Picture a universe where the invisible threads of dark matter don't just connect galaxies, but whisper secrets that guide their very evolution. Until we crack this code, every aligned galaxy stands as a silent challenge to our understanding, a cosmic fingerprint we're only just learning to read. The universe loves to defy expectations, and nothing proves this more than the bizarre case of spinning cosmic filaments. These colossal threads, each hundreds of millions of light-years long, should be among the most inert structures in existence, drifting silently through the void. Yet astronomers have stumbled upon something that shouldn't be possible: filaments that rotate, slowly, subtly, but undeniably, as if some cosmic hand twisted them like a celestial rope. Here's the problem: nothing in our current understanding of physics explains how structures this vast could ever acquire spin. Picture a filament stretching between two galaxy clusters, each cluster pulling with its immense gravity. Normally, these forces should cancel out, leaving the filament stretched but still. Instead, observations reveal gas and even galaxies within some filaments moving as if sliding along a corkscrew, tracing a helical path millions of light-years long. The rotation is achingly slow. A single turn could take billions of years, but its very existence throws astrophysics into disarray. Where would the energy for such motion come from? And how could something so enormous start spinning without tearing itself apart? One radical theory points to the early universe's turbulence. In the first moments after the Big Bang, space might have been a churning maelstrom of quantum fluctuations, seeding not just the filament shapes but also hidden vortices, like invisible whirlpools frozen into the fabric of spacetime. As the universe expanded, these primordial spins could have been magnified, imprinting rotation on structures we now see as mature filaments. It's a tantalizing idea, but there's a catch. Simulations of cosmic evolution rarely predict such behavior, leaving scientists scrambling to tweak their models. Then there's the dark matter dilemma. If dark matter flows through filaments in streams or clumps, its gravitational nudges could torque the gas ever so slightly, like a spoon stirring coffee over cosmic time. Some researchers suggest that asymmetric mergers where galaxy clusters collide off-center might also transfer angular momentum to filaments, spinning them up like a top struck at an angle. But these explanations stretch known physics to its limits, requiring delicate, fine-tuned interactions across scales we've barely begun to map. Even stranger, not all filaments rotate. Some appear perfectly still, while others, seemingly identical in size and environment, exhibit this ghostly spin. Why the discrepancy? Magnetic fields could play a role, tangling with gas flows to induce rotation in some regions but not others. Or perhaps it's a question of age. Younger filaments still accumulating matter might be more prone to twisting motions, while older ones have settled into equilibrium. The implications are staggering. If filaments truly rotate, they could be funneling not just matter but also angular momentum across the cosmos, subtly influencing how galaxies form and spin. It's a reminder that even the universe's grandest structures aren't static, they're dynamic, evolving, and far more mysterious than we ever imagined. Every silent turn of these cosmic threads whispers a challenge, our understanding of gravity, dark matter, and the birth of structure itself might be missing a crucial piece. And until we find it, the filaments will keep spinning slow, silent, and defiant in the dark. Computer simulations of the cosmic web have long predicted a universe teeming with dwarf galaxies, tiny, faint collections of stars that should swarm along filaments like fireflies in the night. According to our best models, these diminutive galaxies ought to outnumber larger galaxies like the Milky Way by a factor of 50 or even 100, clustering along filaments in such abundance that the cosmic web should glitter with their light. Yet when astronomers peer into the depths of space, they find a startling discrepancy. The dwarf galaxies simply aren't there, at least not in the numbers they should be. This glaring mismatch between theory and observation is one of cosmology's most persistent headaches, and it goes by a deceptively simple name: the missing dwarfs problem. The roots of this mystery trace back to dark matter. Simulations show that as filaments formed, dark matter's gravity should have carved out countless small clumps, each massive enough to attract ordinary gas and ignite star formation. These clumps, known as dark matter halos, are the invisible cradles where dwarf galaxies are born. But while telescopes have spotted some dwarfs, they've found only a fraction of what simulations predict. Even accounting for the fact that many might be too dim to detect, the gap remains enormous. It's as if the universe forgot to build half its galaxies. One proposed solution is the too big to fail problem. Some of the missing dwarfs aren't actually missing, they're just too dark to see. The largest predicted dark matter halos should have hosted galaxies bright enough to spot, yet many of these expected giants are nowhere to be found. This suggests something might be suppressing star formation in these halos, leaving them virtually invisible. Perhaps ultraviolet radiation from early galaxies sterilized their gas, preventing stars from ever igniting. Or maybe supernova blasted their gas away before it could coalesce. Either way, these failed giants lurk in the shadows, their dark matter halos intact but their stellar populations tragically stunted. Yet another twist comes from alternative dark matter theories. What if dark matter isn't quite what we think? The standard model assumes dark matter is cold, slow-moving, and prone to clumping. But if dark matter were slightly warmer or more interactive, it might not form as many small halos, neatly explaining the dwarf shortage. Some theories even suggest dark matter particles could collide and annihilate, erasing small halos before they ever had a chance to shine. The implications ripple far beyond missing galaxies. If dark matter behaves differently than our simulations assume, it could reshape our entire understanding of cosmic evolution. And if filaments truly hide legions of invisible, starless halos, they might be far more massive and far stranger than we ever imagined. Every undetected dwarf is a silent question mark, challenging us to rethink the rules of the universe. The cosmic web's most striking feature isn't just its filaments, it's the razor-sharp edges where they meet the voids. These boundaries aren't the gentle fades you'd expect. Instead, they're shockingly abrupt, like ocean cliffs dropping into an abyss, where the density of matter plunges 100-fold in less than 50 million light-years. This defies every simulation. Why don't these transitions blur gradually, the way smoke dissipates into air? The answer might rewrite how we understand the universe's skeleton. Think of a sponge, dip it in water, and the liquid seeps inward slowly, creating a smooth gradient from soaked to dry. That's how matter should behave as filaments give way to voids, yet what we observe is more like cracking ice. One moment you're surrounded by galaxies, the next you're staring into nothingness so vast it could swallow Milky Way's whole. Astronomers call this the void sharpening problem, and it hints at forces we've overlooked. One clue lies in dark energy's relentless push. As the universe expands, dark energy doesn't just stretch space, it might actively evacuate voids, accelerating matter away from their centers like a cosmic tide pulling back from shore. This could sculpt those knife-edge boundaries, leaving filaments isolated like islands in an ever-widening sea. But there's a wilder possibility. Magnetic fields, those invisible threads weaved through filaments, might act like fences, corralling gas and preventing it from leaking into voids. Some observations show charged particles aligning eerily along void boundaries, as if tracing some vast, unseen barrier. Even more speculative is the idea of cosmic sound waves from the early universe pressure oscillations left over from the Big Bang that might have stacked matter into sharply defined layers, like sand settling into distinct bands after a wave. The implications are profound. If void boundaries are this sharp, it means filaments aren't just passively growing, they're locked in a tug of war with the emptiness around them. Galaxies near these edges might experience bizarre tidal forces, stretched into elongated shapes or stripped of their gas entirely. And if dark energy's role is confirmed, it would mean the cosmic web isn't just a relic of the past, it's a living structure, still being carved by forces we're only beginning to measure. Every void's edge is a puzzle written in negative space, a reminder that the universe's emptiest places might hold the sharpest secrets. Filaments in the cosmic web aren't always the straight, razor-thin highways we imagine. Some bend and twist like cosmic rivers, carving elegant arcs across the void. This curvature shouldn't exist. According to our best models, gravity should pull these structures into near-perfect lines, the shortest paths between galaxy clusters. Yet telescopes have caught filaments defying expectations, warping into gentle curves or even sharp kinks spanning hundreds of millions of light years. The question isn't just why they bend, it's what colossal force could possibly flex something so immense. One leading suspect is dark energy, that mysterious force accelerating the universe's expansion. As dark energy stretches space itself, it might not act evenly, tugging harder in some regions, creating asymmetries that nudge filaments off course. Picture a rope pulled from both ends, but with an invisible hand pressing gently on one side, coaxing it into a slow cosmic bow. Simulations suggest this could happen where voids expand unevenly, their growth warping nearby filaments like trees bending in a relentless wind. But here's the catch: the curvature we observe often exceeds what dark energy alone should produce, hinting at forces we haven't yet accounted for. Then there's the wild card, large-scale tidal forces. When galaxy clusters collide, their gravitational wakes might ripple through filaments, twisting them like ribbons caught in a storm. Some curved filaments align suspiciously with ancient collision sites, as if frozen in the aftermath of a cosmic wreck. Even stranger, a few filaments exhibit helical shapes spiraling subtly along their lengths like DNA strands. Could these be relics of primordial spin, left over from the universe's turbulent birth, or evidence of dark matter's hidden currents swirling in ways we've yet to model? But the most tantalizing possibility is the most unsettling. These curves might trace the influence of undiscovered physics. Alternative gravity theories, like modified Newtonian dynamics, predict subtle deviations in how structures form on vast scales, deviations that could manifest as filament curvature. Others speculate that dark matter interactions, or even exotic fields permeating space, might sculpt these bends into existence. Every twisted filament is a silent challenge, a reminder that the universe's blueprint might still hold chapters we haven't learned to read. The deeper we look, the more these curves defy simple explanations. Some appear too smooth for random collisions, too precise for dark energy's push. They're not flaws in the cosmic web, they're fingerprints pressed into the fabric of space by forces we're only beginning to trace. And until we decode them, they'll linger as quiet, elegant mysteries arcing through the dark. Deep in the cosmic web, astronomers have stumbled upon an eerie glow, diffuse radio emissions humming along filaments like ghostly power lines. These aren't the crisp signals of pulsars or the crackle of distant quasars. Instead, they're vast, fuzzy whispers spanning millions of light years, silent to optical telescopes but blazing in radio waves. The strangest part, no one knows what's causing them. These emissions defy every conventional explanation, hinting at processes we've never witnessed or particles we've yet to discover. One leading theory points to cosmic rays, those high-energy particles racing through space at near light speed. When these particles spiral along magnetic fields woven through filaments, they could emit synchrotron radiation, the same process that lights up nebulas. But there's a catch. The emissions are too uniform, too widespread. Cosmic rays should cluster near their sources, like supernova remnants or active galaxies, yet these signals paint entire filaments with eerie consistency. It's as if something or someone left the universe's lights on in places where no switches exist. Then there's the dark matter angle. If dark matter particles occasionally collide and annihilate, they might release energy as faint radio waves. Filaments dense with dark matter could act as colossal antennas broadcasting these elusive interactions. Some models even suggest exotic dark matter forms, like actions or sterile neutrinos, could decay into observable radio signals. But here's the rub. These emissions don't match the predicted patterns for any known dark matter candidate. They're too bright in some regions, too dim in others, as if dark matter itself is playing hide and seek across the cosmic web. Perhaps most tantalizing is the possibility of entirely new physics. Certain filaments emit radio waves at frequencies that don't align with any known process. No known particle, no known magnetic interaction. Could these be traces of primordial magnetic fields, fossilized from the Big Bang and only now revealing themselves? Or evidence of cosmic strings, hypothetical defects in spacetime predicted by string theory, vibrating like plucked guitar strings across the universe? The emissions even seem to correlate with unexplained cold spots in the cosmic microwave background, fueling speculation that they're linked to parallel universes or other dimensions brushing against our own. Yet for all the theories, the radio enigma only deepens with each observation. Some filaments glow steadily while others flicker over cosmic timescales. A few even show polarization patterns suggesting their magnetic fields are tangled in ways no simulation can replicate. It's as if the universe scribbled a message in a language we're only beginning to decipher, one where filaments aren't just structures but living, pulsing entities whispering secrets into the static of space. Until we tune into the right frequency, these ghostly hums will remain the cosmic web's most haunting unanswered question. Dark energy has always been thought of as a uniform force, stretching space evenly in all directions. But what if it has a secret preference for certain places? Recent studies have uncovered something unsettling. The expansion of the universe might not be as smooth as we assumed. Instead, dark energy's grip could be tightening along cosmic filaments, warping these colossal threads in ways that defy everything we thought we knew about cosmic acceleration. One clue comes from measurements of distant supernova. When astronomers track these stellar explosions in different regions of space, they've noticed something unexpected. Galaxies nestled along filaments appear to be receding slightly faster than those floating in voids. The difference is subtle, just a few percent, but if real, it would mean dark energy isn't just a passive backdrop to the universe's expansion. It might be actively woven into the cosmic web, its influence amplified wherever matter is most densely structured. This idea throws a wrench into the standard model of cosmology. For decades, dark energy has been treated as a constant, described by a single number, the cosmological constant, that doesn't care about the universe's structure. But if filaments are somehow supercharging its effects, it suggests dark energy could be dynamic, changing in strength based on its environment. One radical theory proposes that dark energy interacts with dark matter in hidden ways, funneling its repulsive force along filaments like electricity through a wire. Another suggests that the fabric of space-time itself might behave differently in these high-density corridors, stretching more eagerly where gravity's pull is strongest. The implications are staggering. If dark energy truly clusters along filaments, it could mean the cosmic web isn't just shaped by gravity. It's locked in a tug of war with the very force tearing the universe apart. Filaments might act as cosmic accelerators, amplifying dark energy's push in some regions while leaving voids to expand more slowly. This wouldn't just rewrite our understanding of cosmic acceleration, it could redefine how we measure the universe's fate. Distances between galaxies, the timing of cosmic events, even the ultimate destiny of everything might hinge on these invisible threads more than we ever imagined. Yet the evidence remains fiercely debated. Skeptics argue that observations could be skewed by galactic dust or measurement errors. Others point out that simulations struggle to reproduce this effect unless new, exotic physics is introduced, raising the question of whether we're seeing dark energy's handiwork or just the limits of our models. But if future telescopes confirm these findings, it would unveil a universe far stranger than we've dared to dream. One where the cosmic web doesn't just connect galaxies, but actively bends the rules of reality itself. Hidden in the furthest reaches of the cosmic web, some filaments contain pockets of hydrogen so pristine they're practically cosmic time capsules, gas untouched by the turbulence of star birth, untainted by the metals forged in stellar furnaces. This is primordial hydrogen, a relic substance preserved nearly unchanged since the first few 100 million years after the Big Bang. Finding it is like stumbling upon a perfectly preserved fossil, one that holds the chemical signature of the universe in its infancy. But how did these delicate pockets survive 13.8 billion years of cosmic chaos? And what can they tell us about the universe's raw ingredients before anything else existed? These ancient hydrogen reservoirs exist in filaments so diffuse, so isolated, that gravity never gained enough foothold to collapse them into stars. Picture a cloud of gas drifting in a quiet backwater of the cosmos, far from the gravitational tug of galaxies or clusters, so undisturbed that even the shock waves from nearby supernova never reached it. Without the compression needed to spark star formation, the gas remained chemically frozen, its composition mirroring the universe's earliest moments. Spectroscopic analysis reveals hydrogen and helium in ratios predicted by Big Bang nucleosynthesis, with trace amounts of lithium, the only elements the newborn universe could manufacture before stars took over the heavy lifting. Yet these fossil regions aren't just passive relics, they're cosmic gold mines for astronomers. By studying their absorption lines, the way they filter light from distant quasars, we've uncovered details about the early universe's temperature, density, and even how light first escaped the cosmic fog of the Dark Ages. One such filament, discovered in 2018, showed hydrogen so pristine its deuterium levels. A rare isotope of hydrogen matched theoretical predictions with uncanny precision, confirming our models of the universe's first few minutes with real-world evidence. But the real mystery isn't just how this gas survived. It's why some regions avoided contamination while others didn't. Magnetic fields might play a role, creating protective barriers that shielded these filaments from turbulent flows of metal-rich gas ejected by galaxies. Alternatively, their locations in particularly serene stretches of the cosmic web, far from the bustling intersections where galaxy clusters collide, could have left them in a state of suspended animation. There's even speculation that dark matter's distribution might have shepherded these pockets into isolation, its gravitational influence carving out safe zones where ordinary matter could remain undisturbed. What makes these primordial filaments truly astonishing is what they lack: heavier elements like carbon, oxygen, and iron, the building blocks of planets and life. Their absence is a stark reminder that the early universe was chemically barren, a place where the periodic table had just 3 entries. Finding these untouched strands is like rewinding time, offering a glimpse into an era before stars lit up the cosmos, when everything hung in perfect, fragile balance. And as we uncover more of them, they're not just teaching us about the past, they're revealing how rare, how improbable the universe's journey to complexity truly was. Among the most staggering discoveries in the cosmic web are filaments stretching so long they defy the very notion of cosmic time, threads like the Hercules Corona Borealis Great Wall, a filament so vast it spans over 10 billion light-years, dwarfing even the largest known galaxy clusters. These are not mere strings of galaxies, they are titanic bridges of matter, some so lengthy they shouldn't have had enough time to form in the universe's 13.8 billion-year lifespan. If structures this colossal exist, what does that mean for our understanding of cosmic evolution? And could they force us to rewrite the story of the Big Bang itself? The puzzle begins with gravity's speed limit. Matter, even under the relentless pull of gravity, can't clump together faster than the universe ages. For a filament to stretch 500 million light-years or more, its components would have needed to communicate across those distances early enough to coalesce, a process that, under standard models, should take far longer than the cosmos has existed. It's like building a sandcastle the size of a mountain in the few seconds before the tide rushes in. Yet here they are, these gargantuan threads, etched across the sky as if the universe cheated its own rules. One radical solution lies in cosmic inflation, the theory that the universe underwent a fleeting, exponential expansion in its first fraction of a second. If inflation stretched quantum fluctuations to macroscopic scales, it could have planted the seeds for these ultra-long filaments from the very beginning. Picture a balloon inflating so rapidly that microscopic wrinkles on its surface stretch into continent-sized creases, except in this case, the wrinkles became filaments spanning billions of light-years. Inflation would have given them a head start, allowing gravity to refine rather than construct them from scratch. But even inflation might not fully explain their coherence. Some of these filaments are too straight, too uniform, as if sculpted by a force beyond gravity alone. Enter dark flow, the controversial observation that galaxy clusters seem to drift in a preferred direction, as if tugged by something outside our observable universe. Could these filaments be cosmic rivers flowing toward unseen mass beyond the horizon of our cosmos? Or perhaps dark matter's hidden interactions, faster and stranger than we've modeled, wove these threads in ways we've yet to comprehend. The implications ripple through cosmology. If filaments this long are common, they might hint at an older universe than we've measured, or worse, flaws in how we calculate cosmic time. Alternatively, they could be evidence of multiversal collisions, where neighboring universes brushed against ours during inflation, imprinting their signatures as these impossible structures. Every ultra-long filament is a silent challenge, a celestial yardstick measuring not just distance, but the limits of our understanding. And until we unravel their origins, they'll loom as reminders that the universe's grandest designs might still be written in ink we can't yet see. Filaments should be littered with heavy elements: carbon, oxygen, iron, the cosmic shrapnel of countless supernova and stellar winds that ought to have enriched them over billions of years. Yet when astronomers measure the chemical composition of these vast threads, they find a puzzling scarcity, as if someone scrubbed the cosmos clean of its metals. Where did they go? The answer could rewrite our understanding of how galaxies share their wealth, or expose hidden forces acting as cosmic thieves in the dark. Start with galactic winds, those titanic outflows driven by supernova and black hole activity. These winds are supposed to be intergalactic couriers, hurling heavy elements far beyond their home galaxies and seeding filaments with stellar debris. But observations suggest they're far less efficient than we thought. Some metals might stall in galactic halos, trapped by magnetic fields or gravity before they can reach the web. Others could be cooling too rapidly, condensing into dust grains that invisibly cling to denser regions rather than dispersing. It's like trying to spray paint a canvas in a hurricane. Most of the pigment never lands where you intend. Then there's the void's hunger. Filaments bordering enormous cosmic voids show the most extreme metal deficits, as if the emptiness itself is swallowing them. One theory suggests that dark energy's relentless expansion stretches these regions so thin that metals diffuse beyond detection, like dye dissolving in an infinite ocean. Alternatively, primordial gas from the universe's first epoch, still pristine and metal-free, might be diluting the mix, flowing into filaments and washing away heavier elements. But the wild card lies in the unseen. Could there be unknown processes stripping metals from intergalactic space? Some simulations hint at dark matter interactions, where exotic particles collide with ordinary matter, scattering metals into realms we can't observe. Others propose that cosmic rays accelerate metal ions to near light speeds, flinging them so far they vanish from our surveys, the most haunting possibility. That filaments aren't just missing metals, they're hiding them, sequestered in forms our telescopes can't yet see, like invisible ink woven into the universe's blueprint. Every undetected atom is a silent challenge, a clue that the cosmic web's chemistry might be governed by rules we've yet to uncover. Until we solve this elemental heist, the missing metals will linger as ghostly evidence of a universe still keeping secrets. Hidden within certain cosmic filaments, astronomers have detected eerie, rhythmic pulses, vast waves of superheated plasma rippling through these colossal structures like vibrations along a spider's web. These aren't random fluctuations, they're organized, coherent patterns, some spanning hundreds of millions of light years, as if the universe itself were plucking the strings of the cosmic web. What could possibly generate such enormous, synchronized oscillations, and why do they appear only in select filaments while others remain eerily still? One leading suspect is the colossal fury of supermassive black holes. When these monsters lurk at the hearts of galaxies, they don't just devour matter, they spew it back out in jets of plasma moving at nearly light speed. These jets, narrow and focused as cosmic blowtorches, can pierce through galactic gas and slam into nearby filaments, injecting energy like a hammer striking a gong. Simulations show the aftermath, shock waves propagating along the filament, setting the entire structure humming with pressure waves that can persist for billions of years. In some cases, these waves even trigger star formation, compressing pockets of gas into stellar nurseries strung like pearls along the filament's length. But there's another, more violent possibility: filaments crashing into each other. Picture two of these cosmic threads, each weighing as much as 1,000 galaxies, drifting into a gravitational tango. As they graze or collide, their immense gas clouds don't just merge quietly, they slosh, sending tsunamis of plasma rippling outward. These collisions could explain the bizarre double helix waves seen in some filaments, where two parallel strands of gas appear to spiral around each other, locked in a slow-motion dance of destruction and creation. The energy released might even heat the filament's gas to temperatures rivaling the cores of stars, explaining why some filaments glow faintly in X-rays while their neighbors remain dark. Yet the strangest detail isn't the waves themselves, it's their persistence. Unlike ocean waves that fade as energy dissipates, these plasma oscillations seem to sustain themselves far longer than physics predicts. Some filaments act like cosmic feedback loops, where magnetic fields trap and recycle energy, keeping the waves alive for epochs. Others show evidence of resonant frequencies, as if the filament's length and density were fine-tuned to amplify certain vibrations, like a pipe organ playing a single, eternal note across the cosmos. What's at stake isn't just solving a cosmic curiosity. These waves could be the universe's way of transferring energy across vast distances, a hidden mechanism for redistributing heat and momentum without stars or black holes. They might even seed turbulence in regions where galaxies form, subtly influencing how structures evolve. Until we unravel their origins, these ghostly undulations will remain one of the web's most mesmerizing mysteries, a silent symphony written in plasma, echoing through the dark. At the crossroads of the cosmic web, where filaments intersect like celestial highways, something strange happens. Some junctions erupt into dazzling metropolises of galaxies, while others fade into near obscurity. Take the Virgo cluster, a bustling hub of over 1,000 galaxies crammed into a space just 15 million light-years across. Then there's the Pisces-Perseus filament intersection, equally massive yet only sparsely dotted with galaxies, as if the universe forgot to build there. Why do some knots in the cosmic web become cosmic cities while others remain ghost towns? The answer might lie in a cosmic lottery drawn billions of years ago, where the smallest initial differences snowballed into staggering imbalances. Rewind to the universe's infancy. Quantum fluctuations, tiny ripples in the fabric of reality, seeded slightly denser patches where dark matter first began to clump. Where these patches overlapped at filament intersections, gravity had a head start, but here's the catch: not all overlaps were equal. Some intersections happened to inherit multiple dense patches, stacking the odds like loaded dice. As the universe expanded, these privileged knots drew in gas and galaxies at breakneck speeds, while less favored crossings struggled to compete. Simulations reveal a startling truth: a mere 5% density difference in the early universe could determine whether an intersection would one day host a Virgo-like megalopolis or a forgettable galactic backwater. Yet initial conditions don't tell the whole story. Later stage violence plays an equally dramatic role. Galaxy clusters like Coma didn't just grow, they cannibalized. Smaller clusters spiraling into these junctions were torn apart, their galaxies absorbed like cosmic mergers and acquisitions. Meanwhile, quieter intersections missed out on this feeding frenzy. Some were starved by dark energy's push, their supply lines of gas and galaxies severed as expanding voids isolated them. Others fell victim to their own geometry. Filaments meeting at shallow angles delivered matter too sluggishly to ignite a powerhouse cluster. The real enigma lies in the outliers. Certain dense knots, like El Gordo, defy expectations by flourishing in relative isolation, far from the web's busiest intersections. Their existence hints at rogue variables, perhaps primordial magnetic fields channeled extra gas their way, or dark matter's hidden substructure sculpted unexpected gravity wells. One thing's certain: these knots aren't just accidents of scale. They're cosmic archives preserving clues about how randomness and inevitability weave together to build the universe's grandest structures. And every underdense crossing whispers a parallel truth: that for all its majesty, the cosmic web is a tapestry of luck as much as law. Computer simulations paint the cosmic web as a dynamic, ever-shifting structure, filaments surging with turbulence, collapsing into galaxy clusters, or dissolving into voids over mere billions of years. Yet when astronomers peer into the depths of space, they find something startlingly different. Filaments that appear almost frozen in time, their structures eerily stable across epochs. This disconnect isn't just a minor hiccup in our models, it's a gaping rift between prediction and observation, forcing us to question whether we've misunderstood the universe's expansion or overlooked hidden forces holding the cosmic web together. Take the Sloan Digital Sky Survey's maps of distant filaments. By comparing their shapes across billions of light years, and thus billions of years of cosmic history, researchers expected to see dramatic thinning, fraying, or even fragmentation as dark energy accelerated the universe's expansion. Instead, many filaments look statistically identical whether we observe them 9 billion years ago or today, as if some cosmic glue resists the relentless pull of dark energy. Simulations, by contrast, show filaments as transient threads, constantly rewoven by gravity and torn by cosmic expansion. The mismatch is especially glaring in low-density regions, where models predict filaments should have disintegrated long ago, yet they persist like ghostly cobwebs untouched by time. One explanation could lie in dark matter's hidden behavior. If dark matter particles interact with each other even faintly through some force beyond gravity, they might form stable, self-reinforcing structures that simulations don't account for. Picture a filament not as loose sand held together by gravity's weak grip, but as a scaffold laced with invisible cables, its strands flexing but never breaking. Alternatively, magnetic fields threading through these filaments might act like steel rods in concrete, providing rigidity that keeps them intact despite the universe's expansion. But the wildest possibility, dark energy itself might not be uniform. If its strength varies across space, weaker along filaments, stronger in voids, it could explain why filaments resist dissipation while voids grow emptier. This would turn cosmology on its head, suggesting dark energy isn't a passive backdrop but an active player, shaping the cosmic web's survival like an invisible hand tuning the tension of a vast celestial harp. Every stable filament is a silent rebuke to our models, a reminder that the universe's grand design might hinge on rules we haven't yet written. Until we solve this rift between simulation and observation, the cosmic web's stillness will remain one of its most profound puzzles, a tapestry that refuses to unravel. At the smallest scales of existence, where space and time dissolve into a seething froth of virtual particles, lies a phenomenon called quantum foam, a turbulent, ever-changing sea of energy fluctuations predicted by quantum mechanics. Now imagine that same chaotic churn, but magnified to cosmic proportions, woven into the very fabric of the universe's largest structures. Could the filaments of the cosmic web, those gargantuan threads binding galaxies together, be the macroscopic echoes of spacetime's tiniest tremors? It's a dizzying idea, one that blurs the line between the infinitesimal and the infinite, suggesting that the universe's grandest designs might be written in the same quantum script as its smallest breaths. The theory hinges on a radical notion that the universe is fundamentally self-similar, with patterns repeating across scales like a fractal. Just as quantum foam emerges from the Heisenberg uncertainty principle, where particles flicker in and out of existence too quickly to measure, filaments might arise from similar instability writ large. Some physicists propose that the same quantum fluctuations that birthed the cosmic web's initial density variations could have deeper roots, tracing back to spacetime's foamy texture in the first moments after the Big Bang. Picture a microscope zooming in on a fingerprint, only to find another, smaller fingerprint within each ridge, except here, the ridges are filaments and the hidden patterns are quantum ripples stretched across billions of light years. Support for this idea comes from eerie geometric resemblances. Quantum foam's frothy bubbles, though trillions of times smaller, bear uncanny visual parallels to the cosmic web's tangled filaments when simulated at high resolution. Both exhibit a web-like interconnectedness, with voids and threads emerging spontaneously from randomness. Even stranger, certain quantum gravity models predict that spacetime's foaminess could leave imprints on the large-scale distribution of matter, subtle statistical quirks in how galaxies cluster along filaments. Some astronomers are now scouring sky surveys for these fingerprints, hunting for telltale irregularities that might betray quantum origins. Yet the boldest claims go further, suggesting filaments aren't just influenced by quantum foam, they might be its direct descendants. In loop quantum gravity, spacetime isn't smooth but granular, composed of tiny, indivisible units. As the universe expanded, these granules could have knitted together into threads, their quantum entanglement persisting as the filaments we see today. It's as if the cosmos unspooled itself along pre-existing quantum seams, weaving dark matter and galaxies into the grooves of a primordial pattern. If true, this would mean the cosmic web isn't just a structure in space, it's a fossil of spacetime itself, a relic of when the universe was smaller than an atom. Skeptics counter that bridging quantum mechanics and cosmology requires exotic physics still in its infancy. The scales are too vast, the energies too disparate. But tantalizing hints persist. Certain filaments exhibit anomalous coherence, length regions where matter's distribution is suspiciously orderly, as if guided by some hidden correlation. Others show faint, repeating density variations that resemble standing waves, the kind you'd expect if quantum vibrations were stretched to cosmic proportions. Even dark matter's elusive behavior, with its puzzling reluctance to clump below certain scales, might hint at quantum effects lingering in the macroscopic world. Whether these connections prove real or merely poetic, they force us to confront a profound possibility: that the universe's largest and smallest phenomena might not be separate at all, but different verses of the same cosmic song. And if spacetime's quantum whispers truly shape the filaments, then every galaxy, every star, every atom in our bodies is riding the crest of a wave that began before time itself had meaning, a ripple in the foam of creation. What if dark matter isn't the only explanation for the cosmic web's immense filaments? Some scientists have dared to propose a radical alternative: that gravity itself might work differently on cosmic scales, eliminating the need for invisible particles altogether. Theories like modified Newtonian dynamics, or MUND, suggest that at vast distances the familiar pull of gravity strengthens slightly, mimicking the effects of dark matter without requiring its existence. On paper, it's an elegant solution, but when confronted with the tangled reality of filaments, does this audacious idea hold up? MUND's biggest triumph lies in explaining galactic rotation curves, the way stars orbit a galaxy's center at speeds that should fling them into space unless extra mass is present. By tweaking gravity's equations, MUND neatly accounts for these motions without invoking dark matter. But filaments pose a far stiffer challenge. Their sheer length, the way they bend light through gravitational lensing, the peculiar motions of galaxies along them, all demand a force far stronger than MUND's modest adjustments typically provide. Some MUND variants, like relativistic extensions such as TVS, attempt to bridge this gap by introducing additional fields that enhance gravity's reach. Yet even these struggle to replicate the web's observed filament curvature and the sharp edges where filaments meet voids. Then there's the puzzle of colliding galaxy clusters like the Bullet cluster, where visible matter and gravitational effects visibly separate, a phenomenon often hailed as direct evidence for dark matter. MUND proponents argue that certain formulations can mimic this separation through complex interactions between baryonic matter and their proposed gravity-modifying fields. However, when applied to filaments, these models often require implausibly fine-tuned parameters, bending over backward to match observations that dark matter explains effortlessly. Perhaps most damning is the cosmic web's sheer uniformity. MUND struggles to explain why filaments across billions of light-years share similar densities and temperatures, as if sculpted by a consistent, pervasive influence like dark matter. Without dark matter's early gravitational head start, MUND universe would have formed structures too slowly, leaving filaments shorter and more fragmented than what telescopes reveal. Yet MUND isn't without intriguing clues. Certain filament anomalies, unexpected gas motions in sparse regions, subtle alignment patterns among dwarf galaxies align oddly well with modified gravity predictions. Some researchers speculate these might hint at a hybrid reality, where both modified gravity and dark matter play roles. Others see them as evidence that we've only scratched the surface of gravity's true complexity. The debate rages on, but one thing is clear: until modified gravity can fully account for the cosmic web's grandeur, its vast rotating filaments, its missing metals, its eerie stability, dark matter remains the reigning champion. Still, the very existence of this challenge reminds us how much we have left to learn. Perhaps the real answer lies not in choosing between dark matter or modified gravity, but in discovering something even more profound: a new physics that rewrites the rules entirely. The structure of the cosmic web is uncanny, not just in its vastness, but in its eerie resemblance to something far more intimate: the human brain. Zoom out far enough, and the universe's filaments look almost identical to the branching neural networks inside our own skulls. Galaxies cluster like nodes at the intersections of these threads, mirroring the way neurons connect at synapses. the similarities don't stop there. Both systems follow strikingly similar mathematical patterns, with filaments and neurons distributing themselves along predictable fractal laws. It's as if the universe built its largest and smallest networks using the same blueprint. This observation has sparked a wild, controversial question. Could the cosmic web be more than just a structure? Could it, in some unimaginable way, be alive? The idea isn't as far-fetched as it sounds. In complexity science, systems that process information, whether brains, computers, or even ant colonies, often evolve similar architectures. Networks optimize efficiency, whether they're routing electrical signals or gravitational forces. Some theorists take this further, suggesting the cosmic web's filaments might not just resemble a neural network, they could function like one. Dark matter's gravitational pull could act as the input, galaxies as processing units, and the threads between them as axons, transmitting some form of cosmic-scale computation. The universe, in this view, wouldn't just contain consciousness, it might be consciousness, a vast, slow-thinking entity where galaxies fire like neurons across billion-year timescales. Skeptics dismiss this as anthropomorphism, projecting human traits onto the indifferent cosmos. After all, similarity in structure doesn't imply similarity in function. But intriguing hints linger. Certain galaxy clusters emit synchronized radio bursts as if pulsing in rhythm, a phenomenon without clear explanation. Filaments also exhibit strange coherence in their magnetic fields, aligning over distances too vast for known physics to easily explain. Even dark energy's acceleration could be framed as a kind of metabolic rate, driving the system's expansion like a thought unfolding. The most provocative version of this hypothesis comes from integrated information theory, a framework for consciousness that measures complexity. Under this model, any system with sufficient interconnectedness, whether a brain or a galaxy cluster, might harbor some form of experience. The cosmic web, with its near-infinite nodes and connections, would score astronomically high. Of course, experience here wouldn't mean thoughts or feelings as we know them. It might be more like a cosmic hum, a background hum of awareness as alien to human thought as gravity is to a photon. Still, the leap from structure to sentience is enormous, and evidence remains speculative at best. Yet the mere possibility forces us to confront profound questions. If the universe were self-aware, how would we even recognize it? Could the laws of physics themselves be the code of its cognition? And if the cosmic web is truly processing information, what is it calculating? The answers, if they exist, might lie beyond our current science, hidden in the silent, slow-motion flicker of galaxies along filaments older than time. Until then, the web keeps its secrets, its structure whispering tantalizing parallels but no definitive truths, a cosmic echo of the mind or just a trick of the light. The next decade of cosmic exploration promises to peel back the veil on filaments like never before, armed with telescopes so advanced they'll make today's instruments seem like handheld magnifying glasses. Leading the charge is NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Roman won't just observe the cosmic web, it'll dissect it with a sweeping field of view 200 times wider than Hubble's, stitching together the first high-definition map of filaments across billions of light-years. Its infrared eyes will pierce through cosmic dust, revealing how faint dwarf galaxies trace these threads like luminous beads on a string. But Roman's real power lies in its ability to catch the universe in motion. By measuring how filaments warp the light of millions of background galaxies through gravitational lensing, it could finally reveal the true dance of dark matter, whether it flows smoothly through these tendrils or clumps into hidden knots that defy current physics. Meanwhile, the Square Kilometre Array, or SCAR, will listen to the cosmic web's faintest whispers. This sprawling radio telescope network, spanning continents from Australia to South Africa, will detect the faint synchrotron radiation from filaments with unprecedented precision. Previous telescopes caught only the brightest tendrils, like spotting cities from space by their streetlights. SKA will illuminate the backroads, the dim, diffuse filaments where primordial gas might still linger untouched. Its most tantalizing target, the elusive 21-centimeter line, a radio signature from neutral hydrogen gas that could trace filaments all the way back to the cosmic dark ages, long before stars ignited. If detected, these signals would act as time capsules, preserving the moment the cosmic web first flickered to life. Together, these instruments could crack lingering enigmas. Why do some filaments rotate while others don't? Roman's precise galaxy motion studies might catch dark matter in the act of spinning these colossal structures, while SKA's radio eyes could spot magnetic fields acting as cosmic brakes. The missing dwarf galaxies problem could finally meet its match too. Roman's deep surveys may uncover thousands of ultra-faint dwarfs hiding along filaments, or confirm their absence, forcing us to rewrite dark matter's rules. Even the web's ghostly magnetic fields won't escape scrutiny. SKA's polarization measurements might distinguish whether these fields are primordial relics or forged later by galactic storms, settling a debate that's raged for decades. But the biggest surprises will likely come from the unexpected. The last time we upgraded our cosmic vision, with instruments like Hubble and Chandra, we stumbled upon dark energy and supermassive black holes in every galaxy. This next leap could reveal filaments pulsing with dark matter annihilations, or exotic particles streaming along their lengths. There's even a chance we'll spot the cosmic web's missing link, the hypothetical cosmic strings predicted by string theory, defects in spacetime so dense they'd warp filaments into bizarre, knotted shapes. Every observation will be a step closer to answering the grandest question of all. Is the cosmic web just the universe's scaffolding, or something far more profound, a living, dynamic system we've only begun to decode? The data floodgates are about to open. Roman and SKA won't just add chapters to the story of filaments, they might rewrite the book entirely, revealing a cosmos stranger and more connected than we ever imagined. So where does all this leave us? After journeying through the cosmic web's greatest enigmas, from spinning filaments defying gravity's rules, to ghostly magnetic fields older than time, to the haunting absence of galaxies that should exist, we're left staring at a universe far stranger than textbooks ever described. The web's filaments aren't just threads in the dark, they're cosmic puzzles whispering contradictions at every turn. Why do some filaments glow with unseen radio waves while others stay silent? How can pristine gas from the Big Bang survive untouched in certain tendrils, yet vanish without a trace in others? And perhaps most perplexing of all, why does this vast, intricate network mirror the human brain's own wiring so uncannily? Each mystery forces us to confront how little we truly grasp. Take dark matter, the invisible glue holding filaments together. We've mapped its gravitational fingerprints, yet its true nature slips through our fingers like smoke. Or consider those colossal filaments stretching further than physics says they should, as if the universe played by different rules in its youth. Even the web's stability taunts us, standing firm against dark energy's relentless pull while simulations insist it should fray. These aren't minor gaps in knowledge, they're chasms revealing how much of the cosmic script remains unread. And yet, this is what makes the cosmic web so exhilarating. Every unanswered question is an invitation to look deeper, think bigger, and reimagine what's possible. The same filaments that birthed galaxies also cradled the atoms that became us, weaving our existence into the universe's grand tapestry. So the next time you gaze at the night sky, remember, you're not just a spectator, you're part of this web, connected across space and time to mysteries we've only begun to trace. The greatest lesson these filaments teach isn't about dark matter or missing galaxies, it's about humility. For all our telescopes and theories, the cosmos still dazzles us with the unexpected. And that's the beauty of it. The universe isn't a puzzle to be solved, but a story unfolding, with each discovery revealing new questions more thrilling than the last. So stay curious, because out there in the dark between the stars, the cosmic web is still writing its secrets, and we've barely turned the first page.